Good evening, everybody. This is the beginning of everything. I'm going to try in the next hour or so to give you a brief description of the origin and the very early history of the universe. We're looking at an animation here of lots of galaxies. Can we figure out where all of this matter came from? Let's start by just looking at what the universe looks like at the moment. This looks like a simulation. Well, I suppose it is in a sense, but it's more a 3D atlas. It is a model built from the known positions of a few million galaxies. So they've been mapped in the sky and their distances measured, and that has allowed us to reconstruct a 3D model, which we're now flying through, a 3D atlas, if you like, of our local galaxies. We can see that all of the galaxies aren't uniformly spread. They seem to be clustered together. Occasionally they seem to be strung out into filaments. Some regions of the universe appear to be relatively empty of galaxies. And others... Would it be possible to mute? Thank you. So some regions are relatively clustered of galaxies and other regions appear to be relatively empty. There seem to be voids as well as these filaments. So it would be nice to understand where all of this stuff came from. The universe appears to be chock full of galaxies, trillions of them. Each of these galaxies has got perhaps billions of stars, and we'd like to have some understanding of where all of this stuff has come from. Now we know from individual images like the Hubble Deep Field shown here, where we have perhaps 2 or 3 stars in the field of view and everything else we can see here are galaxies. This is a very small field of view in the sky, and from images like this we can deduce that there must be of order 1 trillion galaxies in the observable universe. So let's go through what we're dealing with. I'm talking about the creation of the universe. When did it happen? 13.8 billion years ago. How long did it take to make a universe? About 3 minutes. Where did it happen? Well, you can't really say where it happened. It happened everywhere. And why did it evolve the way it did? Well, because of the laws of physics. And how do we know all this? Same answer, because of the laws of physics. So, not surprisingly, being a physicist, I think that physics can explain everything, and I'm going to see how far we can get trying to explain the creation and the early evolution of the universe. First, a few general comments. Nature is not repetitive. If nature simply did the same thing over and over and over again, life would be very boring. Yes, I know some days felt a bit like that during lockdown, but generally speaking, nature does not repeat. But also, nature is not totally unpredictable. If nature was totally unpredictable, it would be impossible to make any sense of the world whatsoever. So nature actually lies somewhere in between those 2 extremes. In other words, nature is interesting because it is not simply repetitive and it's not unpredictable. So it must be obeying some set of rules. How does it work? What are the rules? And that's what we're asking here. What are the rules of the game for the universe? If we didn't know what a chess game was, we could look at a picture like that and we could ask ourselves, could we figure out what the rules of chess are by looking at that picture? And the answer, I guess, is no. A single static image does not tell us what the rules are. We might have a guess, but it's difficult to tell whether the rules are very simple or the rules are very complicated. Similarly, we can't look at a snapshot of a galaxy taken by, it doesn't matter what resolution we have, if we've got a snapshot of a galaxy, we can't simply look at that and from that deduce how the universe came to be and how galaxies came to exist. If we go back to the chess analogy, we can ask, well, if we can't tell that from a static picture, could we tell it from a movie? Could we watch 2 people playing chess and from that could we determine what the rules of the game are? Well, yes, we would have a chance with that. But of course, with a galaxy, we can't sit and watch that for a few billion years to see how it changes, how it evolves. We guess that it's rotating, but we haven't got the time to sit back and watch it for a few billion years to see how the universe unfolds. So we can't, going back to the chess analogy, take a single image, and we can't take a movie of a game being played. But in principle, what we could do is to take snapshots, or better still movies, of billions of games being played, and if we look at enough different games, we could get an idea of what the rules must be if all of the games of chess being played obey the same set of rules. So instead of looking at one galaxy, why don't we look at, ideally, thousands or millions or perhaps billions of galaxies? If we can look at enough individual objects within our universe, then we can start to build up an idea of what the rules of the game are. But surely it must be very complex. The rules must be enormously complicated. How on earth can we ever expect to explain an image like this? This is just a tiny part of our backyard, a very small part of our galaxy, where there appear to be different stars of different brightnesses and different colours and different clouds of gas with different composition. Surely the rules that dictate how this comes to be must be too complex for us to understand. Well, let's have an analogy. Let's have a mathematical collection of coloured pixels. Perhaps some of you recognise this. It is part of the Mandelbrot set. A mathematical collection of pixels that represent a particular mathematical expression. And if we zoom into a little part of that, and I'm not going to zoom in continuously, let's just take a very small part of this collection of pixels and ask, what happens if we zoom in? Do we find that the pattern runs out? Do we find that the patterns of coloured pixels here start to repeat themselves? Well, they might look rather similar, but the pattern, just like nature, never actually repeats itself. There are some regions which look similar in the sense that some stars look similar to other stars, but they're not actually identical. And similarly, when we zoom into this collection of coloured pixels, we find different colours and different patterns, and sometimes we get the hint of particular repeating motifs, but actually the motifs never repeat. And we can zoom in essentially as far as we like. Now clearly my monitor here and zoom is incapable of representing more than 1 million or so pixels at a time, but the Mandelbrot set is not limited to a few million or a few billion or a few trillion pixels of colour. The Mandelbrot set is essentially infinitely complex, and we can zoom into our heart's content as much as we like, and we will never find an end, and we will never find a repeat. So, if this is a mathematical collection of pixels, then how complicated must the rules be to generate each and every one of the infinite number of pixels that are part of the Mandelbrot set? Well, the equation that generates the Mandelbrot set is that. Z equals z squared plus c. We don't have to worry about exactly what the z and the c represent. The point is, mathematically represented, it is a very simple rule. If we apply that rule, we can generate the entire Mandelbrot set, even though the Mandelbrot set appears to be infinitely complex. So just because the universe looks very complicated when we look out there and we see lots of different structures, planets and stars and galaxies and all sorts of structures, that doesn't necessarily mean we are incapable of understanding what the rules of the game are that generated the universe in which we live. Einstein summed this up. The most incomprehensible thing about the world, and for world you can take that to mean the Earth or the solar system or the galaxy or the universe, the most incomprehensible thing about the world is that it is comprehensible. As the title says, complex is not the same thing as incomprehensible. That's pretty amazing that a bunch of monkeys who fell out of the trees 1 million or so years ago could actually get their heads around understanding the complexity of the universe. But it is possible. The flow of thought that helps us get a grip on the universe goes as follows. Something like 100 years ago, it was observed that galaxies are moving away from each other. The so-called Hubble flow. From that, we conclude that the universe appears to be expanding. Another set of observations, not astronomy related, but experiments here on planet Earth, particle physics experiments such as smashing things together in particle accelerators, tells us about the nature of matter, what stuff is made of, what we are made of. We're made of molecules, molecules are made of atoms, atoms are made of other stuff. So experiments that started again many decades ago and are now continuing with the Large Hadron Collider are telling us about the nature of matter. But to make any progress understanding the universe, we have to make a few assumptions. Basically, we assume that the laws of physics in one place are the same as the laws of physics in another place. If it was not the case, if it was the laws of physics in the UK were not the same as the laws of physics in Australia, or the laws of physics in Alpha Centauri, or the laws of physics in the Andromeda Galaxy, then we would struggle to make any sense of how the universe is put together. We have to assume that the rules of the game apply throughout. Similarly, we have to assume that the laws of physics now are the same as the laws of physics used to be and the laws of physics will be. If the laws of physics change such that the laws of physics today are not the same as the laws of physics tomorrow, then again we will struggle to build any sort of scientific foundation of our understanding of how the universe is put together. So there's no way we can prove those assumptions, it's just that we cannot make any progress at all unless we assume those are true, that the laws of physics are immutable. If we throw all that together, what do we conclude? Well, we conclude that the universe was created in a very hot, dense state 13.8 billion years ago, and ever since that point has been expanding and cooling. And it's taken 13.8 billion years to arrive at the situation we find today. But the big question is, okay, the universe is full of the observable universe. Let's not talk about what's outside that. Let's just deal with what we can deal with. Inside the observable universe, we can see maybe 1 trillion galaxies, which appear to be made up of a few billion or hundreds of billions of stars. Where does all of that stuff come from? Where did all of the matter that we can see today come from? And we can ask the question, well, we need to turn the clock back to understand the origin. How far back in time can we go? If the universe is 13.8 billion years old, how far can we go backwards in time before we have to give up and say we don't think the laws of physics apply anymore? The first billion years of the universe is 13.8 billion years. Well, the Hubble Space Telescope can see distant galaxies and essentially is seeing back in time because it's taken time for the light from those galaxies to reach us. The Hubble Space Telescope can look back to, let's say, the first billion years, and so that's no problem whatsoever. The James Webb Space Telescope will be able to see a little bit further and will be able to see further back in time to perhaps 500 million years after the origin of the universe. So the first billion years is no problem at all because we've got evidence from the Hubble Space Telescope. But could we go back in our minds, as far as the science is concerned, can we think about how things must have been in the first 1 million years? We haven't got any telescopes that will look that far back in time, but can we at least construct a scientific theory which we believe is on reasonably solid ground? The first 1,000,000 years? Yeah, no problem. The first 1,000 years? Yes. What about the first year after the creation of the universe? Do we think the laws of physics we understand as of today still held then? Yes. What about the first day? Yes. What about the first hour? Yes. What about the first minute? Yes. What about the first second after the beginning? Yes. What about the first millisecond? Yes. What about the first microsecond? I think we're okay. What about the first nanosecond, the first 1/1000th of a second? As far as we can tell, we're still on solid ground. What about the first picosecond? What about the first trillionth of a second after the creation of the universe? No, we can't really say we understand what happened prior to that particular point. Before the first picosecond, after what we generally label the Big Bang, the creation of everything. After a picosecond, we are on reasonably solid ground and everything is relatively well understood. But prior to that 1 picosecond, we cannot, in all honesty, say that we really understand and are confident that the laws of physics we understand today held in those very early fractions of a second. Why a picosecond? Well, as I'll mention shortly, because after a picosecond we are able to reproduce the conditions, reproduce the energies that existed here on Earth, and hence we have experimental ways of testing our ideas. The universe was so hot in the first picosecond, we can't reproduce those conditions, and hence we cannot be absolutely sure. So that was a rather long and winding introduction to what it is that I'm talking about here. In the next slide, I'm going to introduce a few basic ideas which we're going to need in order to take a time jump through the first fraction of a second after the Big Bang, the first few seconds of the universe, the first few minutes of the universe. We're then going to have to change tack slightly and change gear to get through in a reasonable amount of time. We're going to fast forward 377,000 years and then fast forward again to the next 13.8 billion years to bring us up to date to the present time. So that's what we're going to cover in the remainder of this talk. So let's deal with a few basic ideas which we need to understand in order for the next few slides to make sense. Some of this you probably already know, maybe some of it you don't. We are made of atoms. I hope that was one of the statements that you're all fairly comfortable with. An atom is a positively charged nucleus surrounded by negatively charged electrons. So we can take atoms and, despite their name meaning indivisible, we can, given enough energy, tear atoms apart and separate them into a positively charged nucleus and negatively charged electrons. If we have still more energy, we can take the nucleus and we can find that the nucleus is not a fundamental particle. We can take a nucleus and open it up and have a look inside, and we find that a nucleus is made of protons and neutrons. We can't do that with electrons. As far as we have been able to tell, you can't take an electron, cut it in half and have a look and see what's inside. An electron appears to be a fundamental particle with no inner mechanism. It's not made of anything else. It is just an electron. A nucleus, by comparison, is not a fundamental particle. It's a compound particle because it's made of other things. Given enough energy, we can break a nucleus down into its components of protons and neutrons. Similarly, those particles themselves are not fundamental particles because, given enough energy, we can take a proton and we can open it up and find that it's made of smaller stuff. It's actually made of particles which we call quarks. Let's not worry too much about the names of these particles. All we need to worry about is that protons are made of stuff, in this case 3 particles which we have labelled quarks, and as far as we know, quarks are not made of anything else. Like electrons, we can't take a quark, cut it in half and ask what's inside. So here we have an implicit energy scale because it takes more energy to break a nucleus apart than it does to break an atom apart. And it takes more energy still to break a nucleus apart. And it takes more energy still to break a proton apart. So low energy to high energy. And as far as physicists are concerned, low energy means low temperature and high energy means high temperature, in the sense that if we've got a load of particles with a certain amount of energy, we can, if we wish, talk about those particles having a temperature as well as a mean energy. So if we've got low energy to high energy, then that's also cold and hot. But remember, the universe, we've assumed, because of the way it's expanding, started hot and is now cooling down. So a time arrow runs from the bottom upwards, which means the universe was built from the bottom up. In the very early universe, the universe was so hot we couldn't have atoms because there was so much energy. Each particle in the early universe had so much energy, they couldn't possibly stick together in atoms. Atoms would be ripped apart, as would nuclei, as would protons. But eventually, the universe would have cooled enough that quarks can stick together to make protons. Still too hot for nuclei, but it is possible to make a proton and a neutron. And if we wait long enough, the universe would cool some further, at which point protons and neutrons could stick together to make a nucleus. Perhaps that would still be too hot to make an atom, and we'd have to wait still longer until the universe had cooled further before nuclei and electrons could get together to make atoms. So this is the basic idea, that the universe was born hot, and as it expanded and cooled down, so we can start to build from the bottom upwards protons and neutrons and nuclei and then atoms and then molecules and then us, etc. Okay, so that's the general idea. So let's start the journey at t equals 0. What happened at the instant of t equals 0? Well, remember, I've already admitted that we don't really know what happened prior to the first picosecond or so. And no surprise, science cannot provide a definitive answer of what happened at t equals 0. There's plenty of theories, there's plenty of speculation, but we cannot prove with any scientific evidence what actually happened at t equals 0. Many people seem to think perhaps it was a quantum fluctuation in which matter and energy, because E equals mc squared, we can talk about matter or we can talk about energy, they're in a sense equivalent. We can borrow energy and we can borrow matter from nothing. Quantum mechanics allows that. Well, that's really weird. How can you get something from nothing? Well, quantum mechanics allows that. And you might say, well, that's a cheat. That means quantum mechanics is really weird. Well, yeah, right. Quantum mechanics is really weird. But that's the subject of a rather different talk. It is possible to borrow something from nothing as long as you don't borrow it for too long. How big can this so-called quantum fluctuation be? Well, it turns out that energy times time has an upper limit. In other words, you can borrow a lot of energy for a short time, or vice versa. You can borrow a very small amount of energy for a relatively long time. It's like taking money out of the bank. If you borrow a small amount of money, then the interest doesn't worry you too much and you can take your time paying it back. But if you borrow a huge amount of money from the bank, the interest is so large, you really have to pay it back very quickly so as not to accrue a huge debt. So it's a little bit like that. It's saying that in a quantum fluctuation, you can borrow energy from nothing, the bank of nothing. You can borrow the energy as long as you pay it back quickly enough that the universe doesn't notice that you've borrowed the energy. So how much energy did we need to borrow to make a universe? Well, it's rather curious, but if you add up all of what we see today, all of the matter energy adds up to a whole load of positive energy, all the gravitational energy is negative, and when you add up all of the negative gravitational energy and all of the positive mass energy, looks like the answer might be 0. So maybe the total energy of the universe is 0, so how long have we got to pay it back? As long as we like. I'm sure that sounds like a cheat, but then so much of quantum mechanics does work out that way. Let's move forward from 0 to a relatively short time after 0. 10 to the minus 35 seconds. The universe is now approximately the size of a golf ball. Correction, the observable universe is the size of a golf ball. We don't know how big the universe is. It could be a lot larger than the observable universe. What I'm saying is that everything that we currently see inside the observable universe, the trillion galaxies made up of a few 100 billion stars each, all of the matter that's currently inside our observable universe used to be a lot closer together. And if you go back far enough to this particular time point, 10 to the minus 35 seconds, everything in the observable universe used to be contained into a volume about the size of a golf ball. Rather difficult to get your head around, but that appears to be the case. Just like a golf ball, the universe is not perfectly smooth. It has dimples in it. Okay, not dimples as such, this is of course just an analogy. But just as a golf ball is not a perfect sphere, so the universe wasn't a perfect sphere. It had variations, tiny variations in density and temperature throughout the volume of the universe. Eventually, given enough time, when the universe is much bigger, this variation in density and temperature that we see in the cosmic golf ball, that would give rise to the large-scale formation of structures in the universe, the galaxy superclusters, the galaxy clusters, the galaxies themselves. Let's move forward to 1 picosecond, 10 to the minus 12 seconds, 1/trillionth of a second. The universe has now expanded quite considerably. In 10 to the minus 12 seconds, the universe has expanded to the size of, let's say, roughly speaking, the solar system. Yes, I know the solar system doesn't exist yet, but just to give you an idea of scale. The universe has gone from a golf ball to the size of the solar system in 10 to the minus 12 seconds. The temperature continues to fall. As the universe expands, the temperature keeps falling. At this particular point, a picosecond, the temperature has fallen to about 10 to the 15 Kelvin. A ridiculously high temperature, but our calculations would indicate that that's approximately the temperature of all the particles in the universe. And what is the universe made of? Well, we've borrowed a huge amount of energy. Sorry, we might have borrowed zero energy, but we've managed to generate mass from that. And what mass do we generate? Well, let's just call the stuff that's in the universe, let's just call it a quark soup. It's lots of different particles, of which there are bound to be lots of quarks. There are bound to be electrons mixed in there as well, and there's probably a lot more exotic particles as well. We know of a number of different particles, but let's just imagine that the universe is full of a soup of particles, and let's just call it a quark soup. All of those individual particles at this particular temperature of 10 to the 15 Kelvin have a certain amount of energy. And the point is that we can reproduce that energy for a given particle. We can give it that amount of energy in a particle accelerator such as the Large Hadron Collider. So if we want to know how particles behave when they were in this state a picosecond after the Big Bang, when the universe had a temperature of 10 to the 15 Kelvin, we can reproduce those conditions by banging particles together with that sort of energy. And that is why, from this point onwards, we have some idea of what's going on because we can test ideas. If we think that certain particles behaved a certain way from this point onwards, we can test it by seeing how those particles behave at those sorts of energies in particle accelerators. And that's why, because it's testable, we think we've got a reasonable idea of how the universe worked from a picosecond onwards. So, whether or not you think about it as borrowing energy or borrowing matter, it doesn't really make a lot of difference because energy and matter are continually exchanging back and forth and back and forth. I've been talking about matter, maybe I should be more explicit and talk about matter and antimatter. Antimatter is a mirror version of matter. Every particle seems to have an equivalent particle of antimatter. For instance, we know that we are made of protons and neutrons and electrons. Well, protons have a mirror particle called an antiproton. Neutrons have a mirror particle called an antineutron. Electrons have a mirror particle called an antielectron. Every particle that we call matter has a mirror equivalent, which we call antimatter. And originally, matter and antimatter are made in equal amounts. So if we take a certain amount of energy, I don't know how to represent energy in a PowerPoint presentation. I'm just going to have a big capital E there to mean a certain amount of energy. So energy can make, through E equals mc squared, a whole load of matter. And that matter will exist in the form of some amount of matter and an equal amount of antimatter. Probably not a tangerine and an anti-tangerine. It might be an electron and an anti-electron. It might be a quark and an anti-quark. The point is, it doesn't actually matter. Energy is making matter and antimatter, and that matter and antimatter will annihilate and produce energy again. And that energy will then go on to make more matter and antimatter. Not necessarily the same particles again. It now could be a hot dog and an anti-hot dog. Well, probably not. It's more likely to be another fundamental particle like a quark or an electron. But the point is, it doesn't matter. Energy makes matter and antimatter. They annihilate, make energy, which makes more matter and antimatter. Back and forth and back and forth. Matter and energy are continually exchanging back and forth. But somehow, and I'll return to this a little later, but somehow matter gains a very small excess over antimatter. And we don't really understand why. You'd think that we would always have the same amount of matter and antimatter, but somehow an imbalance was produced. So the universe is made of a certain amount of matter and a slightly smaller amount of antimatter. Here I've indicated the imbalance is about 10%. It's actually much, much, much smaller than that. It's not 1 part in 10, it's more like 1 part in a billion that matter and antimatter got out of balance. But you can then see what's going to happen. What happens to the antimatter? Well, it annihilates with its counterpart in matter and produces energy. But what happens to that tangerine on the end, that electron or that quark, whatever it happens to be? That matter hasn't got an equivalent because there's not an equal amount of antimatter and matter. So what do we end up with? We end up with a universe which is full of energy, and generally speaking, when matter and antimatter annihilate, they tend to produce energy in the form of radiation. So light, in other words. So we end up with a universe which is full of light, and there's a little bit of matter left over. 1 part in a billion is left over. In other words, there's something like 1 billion photons of light for every particle in the universe. But let's be thankful that that particle is left over, because that's everything we see. That's us. That's the Earth. That's the Sun. That's the solar system. That's the Milky Way. That's every galaxy we can see in the observable universe is made of that little bit of matter that's left over when a certain amount of matter annihilated with a certain amount of antimatter, but the imbalance meant that we had a little bit left over. So be thankful that that's the way it worked out. If that hadn't happened, the universe would be full of light and nothing else. Let's move forward to a millisecond. Matter and antimatter are continuing to pop into and out of existence. Now, protons and neutrons are simply names that we give for what happens when quarks get together. In other words, if we have a certain number of quarks, we don't have to worry about why they're coloured like that. We don't have to worry about why they have the labels U and D. All that matters is when a certain bag of quarks get together, and they do like to get together when the universe is cold enough. Remember, if the universe is too hot, the proton is ripped apart and the quarks escape effectively. But if the universe is cold enough, those quarks can get together, and a bag of 3 quarks on the left, we give the label proton. And if we have a slightly different arrangement of quarks, like the bag on the right, we label that particular bag of 3 quarks, we label that a neutron. We don't have to worry why we've used those words. We don't have to worry what U and D mean. All we care about is the fact that 3 quarks want to live together, and they can do that in different ways. And they can do that and make a proton, or they can do that and make a neutron. And just like energy is making matter and fluxing backwards and forwards, so protons are changing into neutrons, back and forth and back and forth. After about 1 second, the universe, remember, is still expanding and still cooling. The universe, after 1 second, has cooled to about 1 billion Kelvin. That sounds still like a ridiculous temperature, but bear in mind that temperature is not so different from the temperature in the core of some large stars. Now that the universe is only 1 billion Kelvin, It's actually too cold for protons and neutrons to swap back and forth by energy producing mass, mass producing energy, and protons and neutrons not really having any identity. It's now too cold for one to change into the other. Now protons, it turns out, are a little bit lighter than neutrons. Not by much, only by 1 part in 1,000 or so. How do we know protons are lighter than neutrons? Because we can measure them in the laboratory. And remember, we think that a proton billions of years ago is just the same animal as a proton today. We don't think they're any different. So if we measure protons and neutrons now, and we find that neutrons are a little bit heavier than protons by 1 part in 1,000, we think that was the case all those billions of years ago. In this particular graphic and in the next few slides, I will be representing protons as little red blobs and neutrons as little blue blobs. Protons are lighter, and so what happens is more protons are made. Why does the universe make more protons than neutrons? It turns out the ratio turns out to be 3/4 to 1/4. Well, it's because nature always favours the lower energy. This is a sort of, as it were, universal rule, if you'll forgive the pun. If you've got a choice, you always favour the lower energy or the lower mass. One way of thinking of it is the universe can, in a sense, make loads of protons and loads of neutrons. If the protons are lighter, then they're just a little bit easier to make. So it makes more of them. And at the particular temperature of about 1 billion Kelvin, when protons and neutrons can no longer swap back and forth, then that particular temperature dictates that we should have roughly 3/4 protons, 1/4 neutrons. Or I've just taken 16 representative particles. There are 16 bags of quarks here, and it turns out there are 12 of one and 4 of the other. Now we go forward to a couple of minutes or so. Neutrons are unstable, and some neutrons change into protons because of radioactive decay. How do we know that? Because we can watch them in the laboratory. We can do experiments here on Earth now, and we notice that neutrons are unstable. Neutrons on their own will change after a few minutes into protons, and we think that happened in the very early universe. So I showed 16 representative bags of quarks, and I said that we had 12 protons and 4 neutrons. But now, because some of the neutrons have changed, the ratio of protons to neutrons is now, instead of 12 to 4, it's 14 to 2. 2 of those neutrons have changed into protons. And that ratio is now going to determine what the rest of the universe looks like. After a couple of minutes or so, 2 to 3 minutes, the universe has cooled to a balmy 100 million Kelvin. And now it is possible for protons and neutrons to get together. Remember, until this point, it was simply too hot. And if you try and get neutrons and protons to stick together, it was too hot and they would fall apart. But now that the universe has cooled to 100 million Kelvin, it is possible for neutrons and protons to get together. And what we find happens is that the neutrons love to pair up. And the neutrons, the 2 blue particles here, love to pair up to 2 protons. That is a very, very stable structure. 2 blue plus 2 red, 2 protons plus 2 neutrons is one of the most stable structures that we see today. And again, we have no reason to believe it wasn't the most stable structure that could have formed back in this very early universe. So 2 neutrons want to marry up with 2 protons. The other protons would like to do the same, but there aren't enough neutrons to go round. We've married up 2 neutrons to 2 protons, but then we're left with a whole load of bachelors. We're then left with 12 bachelors who haven't got any neutrons to pair up with, so they're left to float around on their own. This particular structure, 2 protons plus 2 neutrons, is either called an alpha particle, or we could describe it as the nucleus of what will be a helium atom. So at this point, we have, out of the 16 bags of quarks that we were originally looking at, we have 1 nucleus of a helium atom and 12 protons, which ultimately will simply be the nuclei of hydrogen atoms. So we have that much hydrogen and that much helium. So this is a prediction of the Big Bang Theory. If we believe that our understanding of energy and matter, and our understanding of quarks, and our understanding of protons and neutrons, and our understanding of how protons and neutrons stick together, then that would indicate that the universe should be full of this much hydrogen and this much helium. It should be, by mass, 3/4 hydrogen and 1/4 helium. After 3 minutes, that's it. You can't change that. The relative abundance of hydrogen and helium is determined at this particular time point when the universe has cooled to this point. And if this theory is correct, the universe should be full of 3/4 hydrogen, 1/4 helium. What do we actually see? When we turn telescopes on the universe and look at how much is out there, what is the universe made of? Well, the universe is made of, roughly speaking, 3/4 hydrogen, 1/4 helium, just as the Big Bang Theory predicts. This is one of the key observations, or the key predictions, if you like, that tell us that Big Bang Theory has something going for it. It makes a prediction which we can test, and it appears to give the right result. If the universe was made in 3 minutes, what happens in the next 377,000 years? And the answer is not much. The universe continues to expand, it continues to cool, but the nuclei that we've made, the hydrogen protons and the alpha particle, or the helium nucleus if you prefer, they drift around, they lose their energy because of the expansion of the universe, but nothing physically changes until we get to this particular point of 1/3 of a million years. At this point, the universe has cooled to about 3000 Kelvin. And that's important for a very interesting reason. At this temperature, the nuclei can hang on to electrons. The nuclei, such as, for instance, helium or an individual proton in the case of hydrogen, that can now hang on to an electron. Before this time, the universe was so hot you couldn't get an electron to stay in the atom. It got stripped off. But now, for the first time, atoms can exist. Nuclei and electrons get together, and the positively charged nuclei and the negatively charged electrons get together, and the universe changes from a plasma of lots of different electric charges to a collection of neutrally charged atoms. And for the first time, the universe becomes transparent, because it no longer has photons of light that are continually rattling off the positive and negative charges, because now the universe is full of gas made up of neutral atoms. And when it becomes transparent, the light can escape. Light that was rattling around like a ball in a pinball machine up to this point is now free to fly around the universe, because the universe is now transparent. And we see that light. At this particular point, when the universe is 3000 Kelvin, what does something look like when it's 3000 Kelvin? Well, if you heat something up to thousands of degrees, it's going to glow white hot. So the universe was white hot back in these days. And so when the light was released, that white light was released. But we now see it stretched out, because remember, we're talking about a long time ago, a fraction of a million years after the Big Bang. The universe is now some 1,000 times bigger than it was back at this point. So the wavelength of light has stretched from visible light being of order microns or so. That light has now stretched 1,000-fold, so that the wavelength is now millimeters. So we don't see it as white light, visible light. We see it with a wavelength 1,000 times longer. We see it as microwaves. That is the cosmic microwave background, sometimes described as the afterglow of the Big Bang. This is the first point at which the light from the fireball of the Big Bang is released and is allowed to fly across the universe. So this is, as it were, an all-sky map, the entire sky around us unwrapped and put onto a projection here so we can see everything. And it's coloured to show that it's not perfectly uniform. Some parts are a little bit hotter, a little bit more intense in the microwave. Other parts are a little bit colder. So it's roughly the same in all directions. In other words, it's very uniform, but it's not perfectly smooth. We see these variations, these small variations in the map, in the all-sky map. And they are the same, or a result of, if you prefer, of the dimples in the golf ball. Remember, when the universe was very small, it wasn't perfectly uniform. It had small variations in density and temperature. And when the universe expanded, those small variations in temperature and density are precisely what we see in the cosmic microwave background. That variation, that what looks like noise in the background, is those dimples. And that's why we are spending time and effort studying the microwave background. That's why we've sent up satellites. It's not too easy to observe from the ground, but with satellites we get a clear view of the cosmic microwave background, and the more precisely we can measure that, the more precisely we can understand the conditions back in that time after the Big Bang of order 377,000 years or thereabouts. So I said that the dimples in the golf ball gave rise to not only the cosmic microwave background, but right at the start of the talk I said that these variations actually gave rise to galaxies. And we can see that not by observing the universe, because we can't see that far back, but if we run simulations of how we think that happened, we can take a part of the universe full of matter but with some variation, not perfectly uniform, but some variation of density, and we can, in a simulation, say, let gravity do its stuff and see what happens. So this is a very large cube of the universe, and then we can run this simulation over a few billion years, and gravity will collapse the structures, collapse the material inside this cube to give us the sort of structures that we see here. We see filaments, we see voids, where filaments tend to cross each other. We see little knots that are particularly bright in this image. That is where galaxies and clusters of galaxies are forming. Gravity is taking the small variations in density, collapsing them down, and eventually the density is high enough for stars to ignite and produce the stars that we see in the galaxies. So this simulation again gives us something which is similar to what we see when we look out into the universe. We see galaxies not uniformly spread in the universe. We see galaxies clustered, and occasionally we see galaxies that appear to run in filaments, and we see some regions which appear to be completely devoid of galaxies. And the more of these simulations we run, the more we understand how we go from the very early universe of being tiny objects such as everything condensed into a very small volume to the huge large-scale structures that we see in the universe today. If we have a look at our local group, there's the Milky Way galaxy right in the centre there, and we see some small satellite galaxies around the Milky Way. There's the Andromeda galaxy over on the right-hand side. So on this sort of scale, just looking at our immediate neighbours, we can see two large galaxies and a large number of smaller galaxies. If we expand the scale to see beyond the local group, then the local group is now in the centre of this region, and we can see that we are part of a cluster that, roughly speaking, seems to indicate that we're on some sort of a filament, in that we have a particular structure here of particular clusters, the Virgo cluster, for instance, the Fornax cluster, etc. They seem to be strung out onto this filament, much like we would see if we did a simulation which predicts that we would get a cosmic web of filaments and voids. Again, if we go out another scale, we see that again we're here right in the centre and this filament, and we see that there are some regions which don't seem to have much in the way of galaxies at all, these voids. And again, all of this structure, the filaments, the voids, the web-like structure that we see when we map out the galaxies, this is all a result of the fact that the original cosmic golf ball had small variations which ultimately led to gravitational collapse into the structures we see here. On a large enough scale, the universe looks like this web structure, sometimes called the cosmic web. It's a sort of foamy structure. And if we were to zoom into one small part of that, we find filaments that are crossing each other, giving us a bright knot here. And if we zoom into that, we find that knot is actually a cluster or a supercluster. And if we zoom in further, we can see perhaps individual galaxies on a scale of order megaparsecs. And this is the result not of observation, this is the result of simulations trying to understand how we can marry together observations of galaxies around us that seem to be arranged in particular structures with the large scale, we assume on a large enough scale, the large scale uniform structure of the universe. And if we look at one simulation in particular, this is now a little bit old. The Millennium Simulation, as its name implies, was a simulation carried out at the turn of the millennium, so this is now 20 years old, but it illustrates quite nicely that if we zoom in from the large-scale foamy structure of the universe, we see more and more detail as to what these filaments are made of. We see a few voids, these dark areas that you see here, and if we zoom in to where some filaments seem to be crossing each other, there we get the highest densities. This is where gravity has taken hold and taken all of the matter in a particular region and condensed it down until the material is dense enough for stellar ignition to start to fuse hydrogen into helium. So we have the birth of stars, and then the stars are grouping together into galaxies. So we still need to understand this very early process. How did the first stars ignite? How did the first galaxies get made? But we have now some understanding through simulation in terms of how our local structure relates to the large-scale structure of the universe, on the scale of billions of light years. So what about the next 13.6 billion years? Well, if we understand hydrogen, if we understand that in the first 3 minutes we can generate all of the hydrogen, okay, yes, we've got helium as well, but hydrogen is the main fuel that fuels stars. If we can understand that in 3 minutes we can generate shed loads of hydrogen, then we have a pretty good chance of understanding galaxies and individual stars. And if we can understand stars, then we can understand planetary systems and trees and mountains and snowflakes and rainbows and cats and okay, probably not cats. I'm not sure we'll ever understand cats. But if we understand the origin of hydrogen, then there's a logical sequence to, starting with hydrogen, everything else in the universe. Yes, I admit that there are some details of cosmic evolution to be worked out, but you get the basic idea. So let me just remind you of this rather silly timeline that goes from ridiculously short times on the left to the age of the universe on the right. So we don't know what happened at t=0, but very early on in the universe, everything that is now in the observable universe used to be in a volume not much bigger than a golf ball. And those variations ultimately led to the structures we see today. The universe, if we borrow energy, we can make matter, and the early universe was a soup of lots of fundamental particles. We call it a quark soup, but it's actually a lot of fundamental particles, including quarks and electrons. Eventually, the universe got cold enough for some of those quarks to get together, and a bag of 3 quarks we call either a proton or a neutron, and they started to form at the level of a few seconds. After a minute or 2 or 3, those protons and neutrons could get together, and they love to form helium, but what's left over is the main content of the universe, hydrogen, individual protons, which eventually will capture an electron and make neutral atoms. That happened about 1/3 of a million years after the Big Bang. And as soon as nuclei capture electrons, we have atoms, which means the universe is neutral. It's no longer a plasma of positive and negative charges. So the universe becomes transparent and the light is released. And we see that light as the cosmic microwave background. We still have a little bit of thinking to do because we don't really understand how we go from that point to the first stars. So I'm sort of skipping over that as an irrelevance, but that is currently a hot area of research is how did we go from an early universe which was relatively uniform to how did the first stars ignite, how did the first galaxies form? That's one reason that we're putting up the James Webb Space Telescope, to look back in time as far as possible, back to the earliest, hopefully few 100 million years, to try and understand that early galaxy formation. And now, of course, we can look at galaxies around us, and we can look at more distant galaxies to get an idea of how galaxies were formed billions of years ago. The further we can see, the further back in time we're looking, the closer and closer we can get to those dark ages when the first stars were born. So the jigsaw is not complete by any means. Yes, we've found some corners and edges, but we still have some fairly serious questions that I haven't addressed in this talk. Why did matter win over antimatter? Where did that imbalance come from? We know by looking at particle physics there are some asymmetries, but what caused the initial asymmetry? We can measure it to some extent in modern accelerators, but what caused the asymmetry? Why did matter win over antimatter to give us this 1 in a billion left over, which is you, me, and everything else we can see? I haven't talked about dark matter, which causes the galaxies to rotate at a speed which doesn't look right, according to what we see. When we add up all of the mass of all of the stars we can see, all of the gas we can see, it appears there's more stuff out there than we can account for. Also, what is dark energy? The universe is accelerating its expansion. We might expect that as it expands, gravity should slow the expansion down. Surely that's what we would expect. But no, it appears that the expansion is not slowing, it's actually accelerating. And we assume the existence of this weird stuff called dark energy to try and explain that expansion. So I labelled this talk The Beginning of Everything, but I tried to make it clear that I was talking about everything that we can see in the observable universe. All the stars, all the galaxies. All of the ordinary matter in the observable universe is what I was talking about. But all of the ordinary matter in the observable universe, which I called everything, is not everything. All of the ordinary matter is only 4% of everything. The other 96% is dark matter and dark energy, and they are still a bit of a mystery. But that's another story. Thank you for listening.
Thank you very much, Steve.